Hello and welcome back to Calculus 2, section 7.3 on hyperbolic functions. This is the last section of chapter 7, and the next thing we do should be the exam, or if you don't vote that way, whatever, right? So, what are hyperbolic functions? So, 200 plus years ago, one of the greatest mathematicians of all time, Leonhard Euler, figured out the connection between exponential functions and trigonometric functions. So he wrote the formula where you can write sine x as e to the ix. I is the complex square root of -1. So e to the ix minus e to the minus ix divided by 2i, and cosine x is e to the ix plus e to the minus ix divided by 2. No I in this one. There are a couple of formulas that you can, combine these things in and so on, but the interesting thing is that every single calculation that you can do in trig course, which includes the identities, can be replaced with the E definition for sine and cosine. So if you want to solve the identity or prove the identity, let's say sine 2x equals 2 sine x cosine x, or sine squared x plus cosine squared equals 1, you can actually prove those identities by replacing sines and cosines with these. So those of you that are interested in mathematics might be going to electrical engineering and so on, or high tier computer science if you are going to go graduate school eventually. Those exercises would be very beneficial to you to do on your own time. Pick, obviously, very simple trig identity. You should do the sine squared plus cosine squared one, and show that the algebra works out, keeping in mind that I squared is -1, obviously, and all the shoveling of these e's is just algebra, right? Now, what Euler realized is that he can have a whole new family of functions, if he just removes I. So literally go in and just erase each I in these two definitions, and he found that those new functions have similar properties to trig without actually being a trig. Now, that's a huge deal because trigonometric functions are periodic, which means over time they repeat. You know that a sine graph is a wave that goes forever. When you chop it up into smaller pieces, that piece keeps repeating. That's what means to be periodic. The tangent graph does the same thing, right? And you can draw 13,000 of those if you want. They all look the same, and they stack next to each other, right? So that is what it means to be periodic. And you can use it to show any kind of cycle, right? 7 days, the shopping cycle, and then you can talk about the full moon cycle and waves and a whole bunch of that stuff. But once you remove I, the property of function being periodic disappears, and we enter the realm of what he called hyperbolic functions. Now, the important part is to, even though these functions carry same name as trig functions, you have to understand tonight that they are nothing like trig functions. Number one reason, they are not periodic. Your cosine hyperbolic x is going to look something like a parabola, right? That's it. Parabola is not periodic. You just get one of those u's, and that's it. There's not a next one and the next one and the next one. It's just one u. So all of the hyperbolic functions, and there are 6 of them, will be having very similar names to your trig functions without being periodic, without having those properties. But they will also have identities, and those identities will be annoyingly close to the trig identities to the point where you might start confusing them. So please, either on a note card or a cover of your notebook, make sure that you have a blurb for trig, which we are going to need in chapter 8 and beyond, and then blurb for hyperbolic functions, which will be resurrected in differential equations eventually, okay? So half of your solutions will be trig for certain equations, half will be trig, and half will be hyperbolics. So you need to know this stuff, but right, especially electrical engineers, and I will show that at the end. So this is your trig, and now to create hyperbolic, sine hyperbolic of x is e to the x minus e to the negative x over 2, and cosine hyperbolic of x is equal to e to the x plus e to the minus x over 2. These are the 2 formulas that you absolutely must memorize or you're going home. No, or I'm calling the police. All right. No need to run now. I'm not calling until after the test, all right? So, these are your definitions for sine hyperbolic x. So this one over here, sine hyperbolic x. Cosine hyperbolic x. That's the way you read them. Good. 2 out of 6 done. So what are the other ones? Well, what do you think the tangent hyperbolic is? Of course. Very good. So tangent hyperbolic x must be sine hyperbolic x over cosine hyperbolic x, or in terms of ease, you have e to the x minus e to the minus x divided by e to the x plus e to the minus x. Cotangent hyperbolic x is 1 over tangent hyperbolic x, which is cosine hyperbolic x over sine hyperbolic x, which is e to the x plus e to the minus x over e to the x minus e to the minus x. How about secant hyperbolic x? Yes. 1 over cosine hyperbolic x, which would be 2 over e to the x plus e to the minus x. Very good. Cosecant hyperbolic x is 1 over sine hyperbolic x, which is 2 over e to the x minus e to the minus x. And I'm going to put these into the blue box because all of these, in terms of their E definitions, are derived if you memorize the top 2. Cool? All right. Here we go. Writing in blood, all capitals. Hyperbolic functions are not periodic. Therefore, they are nothing like trig. Now, since you all have ability to click on a computer, hopefully, I am not going to print and distribute this. If you care, get one. Yes, Chewbacca? Here are the 6 graphs for 6 hyperbolic functions. As you can see, none of them repeat. Do we all see cosine hyperbolic looking like a parabola? Right? Tangent hyperbolic looks like a cube root of x. It's not, but it looks like. Did anyone take statistics? Bell-shaped curve can be approximated by secant hyperbolic, as you can see over there on the graph. Since these graphs, now you have your 1 over x lookalikes and so on, right? So these hyperbolic functions, so if you care, right, you punch this into Google, you can do it now, and there's the printer right there, and you have your graphs. Sometimes one of your possible project problems is to print a cosine hyperbolic graph between, I don't know, -5 and 5, and then trace that with a piece of wire, and then cut the wire to the size of the graph, then use the length formula using computer to integrate to calculate the length of the line that it's printed. Now, because you bent the wire directly on the line and cut it on the, you can straighten that against the ruler, and then you can say that your measured length of the wire plus the calculated length of the wire are almost the same, because there is going to be some error. Just make sure it's not error of 100%. Right? So it's going to be 1% error or something like that, to show that you guys have a reasonable error, right, for that one. So these are your graphs, and the reason why we obviously study these is differential equations. I told you this course is a prereq, heavy prereq for DPQs. And that cosine hyperbolic graph is used primarily in electrical engineering to calculate the sag of the power cables. You all know that the power cables are not stretched into tension between the 2 towers, right? Because if it is, what happens in the winter with Y? In the winter, what happens with objects in cold? They shrink, yes. So if there is no sag, right? If there is no sag, if it's straight, when it starts shrinking, it's either going to snap or rip the tower out, right? Depends on how well you put it right together. So you introduce sag, but if you put too much sag, then the truck passing underneath is going to, right, rip it apart. So there's just to have to be a perfect amount of sag, right? And every cord, chain, anything you hang is not a parabola, it's cosine hyperbolic. So electrical engineers, if you go high power and so on, that's your calculation. Now obviously you will have in your textbook problems with those bridge cables, so civil engineering, right? If you have cables with the bridges and so on, that's your cosine hyperbolic. And you can also have for civil engineering, make an arch or, take that thing and just, upside down with a minus sign. It flips, and then it becomes some kind of arch that you can introduce in your building and so on. So, a lot of use for these. I am not going to spend additional 30 minutes talking about domain and range, because if you have graphs, if you care to print this out and maybe staple it to your notes, you will know that domain and range for sine hyperbolic is negative infinity to infinity. Cosine hyperbolic domain is negative infinity to positive infinity. Range is 1 to infinity, right? So you can read domain and range off of the graph. You can learn what the graph looks like, and all it takes is to type in Google what I did, hyperbolic functions graphs. This image is first image that I clicked on. It's printed right there, and you're done. So hyperbolic functions are not periodic, and I will put here in the notes. Well, if I say Google graphs, then I am not fair to Bing, right? So, and I don't want to say Bing graphs. So, get graphs online. Good. The next order of business is to take a look at, so now we're starting part 2 of the lecture. Next order of business is to take a look at hyperbolic identities and how to prove them. This is going to be one of your problems for upcoming exam for sure. So, hyperbolic identities. As I said before, they will be annoyingly close to trig identities, and the word annoyingly is very carefully used because it's gonna be very easy to confuse the two worlds. So I'm going to list all of the identities that you might get as a problem to work out as a proof, but the formulas are given, and then you just work out the E proof of the problem. So you are replacing sine and cosine hyperbolic with those E definitions, and you are shoveling algebra around until left side equals the right side. Standard math proofs, nothing special. So here we go. Cosine hyperbolic squared x minus sine hyperbolic squared x equals 1. What was the trig formula?
The same thing except h and it's a plus.
Yeah. The trig one was sine squared plus cosine squared equals 1. This is cosine squared minus, right? Next one, 1 minus tangent hyperbolic squared x is equal to secant hyperbolic squared x. Yeah. The trig one is tangent squared minus 1. I know. I promised, right? Cotangent hyperbolic squared minus 1 of x minus 1 is cosecant hyperbolic squared x. Also flipped. Now we have those sum formulas. You remember sine x plus y and cosine x plus y? They were really long. Let's go. Cosine hyperbolic x plus y is equal to cosine hyperbolic x, cosine hyperbolic y, plus sine hyperbolic x, sine hyperbolic y. What was for your trig? This was a minus. Sine hyperbolic x plus y. This one is the same. Sine hyperbolic x, cosine hyperbolic y, plus sine hyperbolic y, cosine hyperbolic x. That one is the same. Oh, you're going to love this one. Cosine hyperbolic 2x is equal to sine hyperbolic squared x plus cosine hyperbolic squared x. I'm just going to write something in blue. Look at this. Cosine 2x is equal to cosine squared x minus sine squared x, and sine squared x plus cosine squared x equals 1. Now look at this one and that one and the blue. Yeah, visually you see how they swapped, right? For trig, this answer is here and this answer is there. For hyperbolics, they're swapped with the answers. You see how close they are? That's what I said, unknowingly close. Unknowingly close. So for this section, you hopefully either know your trig identities insanely well or not at all, right? If you're kind of familiar with them, it's not going to be pretty sorting this stuff out, which world is where, right? But you will need the trig identities in chapter 8 a lot and chapter 12 as well. So, yeah. All right, so what else? The next one is the same. Sine hyperbolic 2x is 2 sine hyperbolic x cosine hyperbolic x. And finally, we have the power reducing. You absolutely must memorize, otherwise you can't integrate. Remember that I told you that you will have to memorize the trig power reducing so you can do trigonometric integrals. You must memorize these two. Cosine hyperbolic squared x is cosine hyperbolic 2x plus 1 over 2, and sine hyperbolic squared x is cosine hyperbolic 2x minus 1 over 2. These formulas are swapped. It's 1 plus cosine and 1 minus cosine for trig. So they are very, very close. Note that pretty much every of these formulas is listing cosine first and then sine. For hyperbolic functions, cosine is the preferred one because it has much higher application. And sine is like, yeah, we use it when we must. Where for trig, we all run to sine and we use cosine when we must, right? You see that two worlds are completely swapped. Now, I will ask you to pick any of these formulas, and I'm going to flex a little bit here, right, to do those e-proofs. So, pick one. 1, 2, 3, 4. Sine hyperbolic x plus y. Oh, put your notebook sideways because I can do this.
It's pretty big, right?
That's how it goes. Sine hyperbolic x cosine hyperbolic y plus cosine hyperbolic x. No, lies. No, yeah, it was good. Cosine hyperbolic x sine hyperbolic y. We are going to replace every single sine and cosine hyperbolic with their E definitions. Whatever is following that as the argument is going to be shoved into exponents of e's. So let's go. Sine is e to the x plus y minus e to the negative x plus y divided by 2. So I hope you see that x plus y is now exponent of e. That should be the same. I put the question mark right there. That should be the same as sine is e to the x minus e to the minus x divided by 2. Cosine is e to the y plus e to the minus y over 2 plus cosine is e to the x plus e to the minus x divided by 2, and sine is e to the y minus e to the minus y over 2. So now we are going to FOIL on the right hand side. So E, actually, let's see if it works or it explodes. Can I do this?
Boom! It exploded.
Good. There we go. Now, do we all see that? Just over 4, 2 times 2. Now FOIL. E to the x times e to the y, same base, exponents add, right? So e to the x plus y. Then plus e to the x minus y. Then minus e to the minus x plus y. And then minus e to the minus x minus y. Now it's time to color code these things. Plus if you didn't listen to put the notebook sideways, now you get to pay the price. I don't want to generate extra paper because then when I go and export this for the PDF to upload, it makes it really small and hard to read. So I'm going to use the new line, but I wasn't joking when I told you turn the sideways. So here we go, e to the x plus y, when you multiply this one and this one, because same base, exponents add. Minus e to the x minus y, when you multiply these two, e to the x minus y. Then plus e to the minus x plus y, and finally minus e to the minus x minus y over 4. E to the x plus y minus e to the minus x plus y in parentheses divided by 2 is equal to, and now I have a single common denominator of 4 for both of these. These two terms are the same, e to the x plus y, so I have 2 of those. 2e to the x plus y then e to the x minus y minus e to the x minus y, they're gone. And so are these, color coding the cancellation. Are we all agreeing on that? Perfect. Minus 2 times e, and now you get to factor a negative, well, minus x minus y, and now factor negative in the next line. So e x plus y minus e minus x plus y divided by 2 should be the same as 2 times, factor the 2 out, you get e to the x plus y minus e to the minus x plus y, everything divided by 4. So now this cancels, and yay. This is how you do proofs. They will give you different examples in homework, and they will make them interesting. You know what I mean, right? Let's take a look at the interesting homework problem where you have to shovel these types of proofs. Beautiful. Problem 14, and then we can move to calculus. Problem 14 says, prove the identity, blah, blah, blah. 2 sine hyperbolic of ln of secant x equals sine x times tangent x. No hyperbolics. These are the trig functions. So what do we have? We have hyperbolic functions, logarithmic functions, and trigonometric functions all on a pile, and we are going to do that through exponential functions. Right? They're kind of missing a square root there, and we're good, right? We pretty much covered everything in one problem. All right, so we know what to do, right? We are going to write sine hyperbolic and use this argument as the exponent. And then we see e and we see ln, and those cancel, and we're happy, right? So this looks disgusting, but actually ln is awesome to have over here. So 2 times e, well, that will be over 2, right? 2 times e to the ln of secant x minus e to the minus ln of secant x should be equal to sine x tangent x. 2 and 2 cancel on the left. ln kills e's. And now you have secant x minus 1 over secant x should be sine x tangent x. So ln and e cancels, secant is there, minus ln cancels. So this minus, we did this last class, I did write the formula down again, the p rule, where the negative 1 goes as the exponent of secant and makes secant 1 over secant, right? And what's 1 over secant? Cosine. Very good. So secant x minus cosine x. And now we transform this problem into a pure trig identity problem where the left-hand side is going to be secant. You write as what? You write secant as 1 over cosine x minus cosine x over 1. And then you figure out common denominator. So we need times cosine for common denominator becomes 1 minus cosine squared x over common denominator of cosine x. And what's 1 minus cosine squared? Very good. So now you have two signs on top multiplying. Split those. And from here should be clear that you have sine x tangent x equal to sine x tangent x. There we go. So these problems could be annoying if they want them to be, right? But they're all solved the same way. And that way is you replace every sine hyperbolic with e minus e, right? Every cosine with e plus e. Whatever the argument of sine hyperbolic and cosine hyperbolic is, the argument is the stuff in parentheses. That goes Control C, Control V into the exponent of e's. And that's it. So those are identities. Let's take a short break. When we come back, part 2 on hyperbolic functions, calculus of hyperbolic functions. Still 7-3.